same questions. Number. Okay, so I'm going to, if those of you who have version 1, that's the version I'm going to follow. All the problems will work the same way, so if you had a version that the numbers were slightly different, you can kind of figure it out. You do have on your Scantrons, except for, I think it's the Tonkawa side version 3, one of them on my key, the Scantron didn't pick it up initially. So there's a little X by it, but I'm pretty sure I got the correct, you'll see the correct answer on the Scantron. Otherwise, the correct answers are listed on the Scantron for the A, B, C, D, and E, except for one of you did it in pen, and one of you circled the A, B, C's, and D's. Scantron doesn't like pen, and the Scantron doesn't like circles. So, so you'll see the missed ones. I've pretty much gotten the correct answers on the missed ones on those 2 Scantrons. I did go back through and get partial credit. If you drew a good picture, you got at least a point on partial credit. So that's why there's a bunch of partial credit out there. If I could tell from your work that it was a math error, then you got most of the credit for the problem. So there were, so a bunch of you did get a bunch of extra points for partial credit. You will ask me at the end of the semester if there's a study guide for the final. You now have part 1 of your study guide for the final. Your past tests, quizzes will all be study guides for the final, okay? All right. So let's start going through the test. And you do get to keep the test. I don't like the paper. My office has got enough paper in it. I don't need any more paper. Okay, so this is the baseball problem where you have a ball leaves the bat with a speed of 43 meters per second at 45 degrees above the horizontal. So basically what happens is we're told that it's 1 meter above the ground. We're going to go off with an initial velocity of 45 meters per second. And we want to know if it's going to go over a 5-meter fence. And we're told that this distance is 137 meters. And we wanted to calculate how far it goes above the fence. Okay, we want to calculate how far it goes above the fence. So first thing you want to know is I've got to figure out the time. Time is going to be the distance divided by the velocity. But my velocity is at an angle. This is a 45-degree angle. So my velocity in the x direction is going to be the velocity times the cosine of the angle. My velocity in the y direction is the velocity times the sine of the angle. And that's where most of you who missed this one messed up. You didn't take into account that I had to use the components of the x and the y. Now there are some of you that got the components of the x and the y, and if you did, you got partial credit. So you got partial credit for the picture. You got partial credit for breaking up the velocity. And then what we ended up doing is do the 137 divided by my 45 meters. This is in meters. This is in meters per second. Cosine of 45 degrees. That gives you 4.5 seconds. So that's the first part of this one. Then my distance, and this is going to be the height, is going to be my velocity times the sine of the angle times the time minus gravity divided by 2 times time squared. And when you do that, you end up with 136.8 minus 99.225. And that gives you 37.5 meters. But that's not the question that was asked. The question that was asked is, how far above the fence am I above the fence? I have to take into account that this is 1 meter. So my fence is 4 meters. So I have to subtract 4 meters to get my final answer, which is 33.5 meters. So this one was one of the harder problems. So if I'm taking a test, okay, and this one actually takes a little bit of time, you don't necessarily have to do the test in order. You could have flipped through and saved this one for later because it was going to eat up your time a little bit. On the other test, it fell a little further back in the test. So, by the time you got there, you probably were, you had a little bit of extra time. But that's why I tell you that, because the next question was, Jeff throws a ball straight up. For which situation is the vertical velocity 0? So if we got a ball that's going straight up, coming back straight down, I have a velocity going up, I have a velocity going down. My velocity at the top, we know, is equal to 0. And so this one, I would just circle at the top. Couple things. If I have a velocity and it's 3 meters per second, and I have a velocity that's minus 4 meters per second, the positive tells me I'm going in that direction if I'm doing left and right, and the negative says I'm going in this direction. The negative is going to tell me direction, okay? The positive and the negatives tell me direction, not that one is less than the other. In fact, this one has a higher velocity than that one in terms of magnitude. This one is just going in the opposite direction. So if I use up as positive, and a lot of times I may change my direction, my positive and negatives, to make my problem simpler. But if up is positive, negative would be in that direction. So the negative sign, when I'm dealing with vectors, like velocity, acceleration, forces, that's going to tell me direction. And it doesn't mean that one is less than the other. It just tells me direction.
The question involved a bit above, like, going a distance. That's not one of the answers on the test. Well, the answer was 42.2.
It this one, it depended upon your version.
Oh.
Your numbers may have been slightly different. Some people may not have had 43 meters per second, may have had a different number for your velocity.
I have 45 meters per second.
Okay, but this is the baseball, leaves with the bat speed, and it is one of the answers on the test. So just double check and make sure you're got the right question. All right, this one, we've got, okay, folks, question here. I have a ball on the edge of a table. How many times have we seen the ball going off the edge of the table?
Lab.
Saw it in the lab. Think this one, if this one is that we said that's going off at 0.27 meters per second. I think those are the exact numbers I used on Friday of last week, or Friday the right before the test, to do an example problem. So we got the ball that's going off of the edge of the table. It's going to land. We're told that the time is 0.3 seconds. And we want to know the height of the table. So the height of the table is going to be, negative g over 2 times squared.
Why is it
is that just the equation?
Well, this one, I could have said it's h is equal to g over 2 because I'm dealing with this direction, but if I'm going to use negative g for my acceleration, I need to have that negative there. Otherwise, I'm going to end up with a negative here, and when I do my t squared, I end up with a, it's just how you want to work the problem. But I plug in my numbers, 9.8 divided by 2 times 0.3 seconds squared gives me 0.44 meters. So test taking, kind of thinking through the test, if you see the problem in lab, if you see the problem on a quiz, if you see the problem in class, odds are you're going to see the problem on the test. Also, this is the same type of problem as my airplane problem when we were dropping the package. So we've seen this problem several times. So it's just a way to know what are my odds of what problem am I going to see on the test. This is an example in the book. Did it as a lab. We see this problem a lot. So if you saw the problem a lot, odds are you're going to see it again. This one is, which of the following is not a vector quantity? Acceleration is a vector quantity. Velocity is a vector quantity. Force is a vector quantity. Displacement, I have direction associated with displacement. So that one's a vector quantity. Mass is not. Mass is not. We're given point A. Point A is 3, 5, and we're given point B. And point B was 3, 10. We wanted to know the distance between the two. This one was kind of straightforward because it's both on 3, so it's just 10 minus 5. It's just going to give me 5 meters. I could have done the square root, do the difference between a1 or x1 minus x2 squared plus y1 minus y2 squared. Take the square root of that. That will give you a distance. But this one was a little straightforward just because it was both in the plots. And you can plot it. So if I did my x is 3, this one was going to be at 3. There's my 5 and there's my 10. This one was going to be here, and that one was going to be there. It just is a matter of which way you jumped into the problem. We have a city uses 7.0 times 10 to the 9 gallons per day. And we wanted to know, and we wanted to end up in gallons per minute. So what we're going to do is, I got to get 24 hours in a day. And there are 60, oops, put that one in backwards. That's why we use our unit analysis. So I'm going to just rewrite it out. 7.0 times 10 to the 9 gallons per day. I want cancel out days, so I want days on top. I want hours on the bottom. I'm going to want minutes on, or hours on top, minutes on the bottom. So this is 1 day is 24 hours. 1 hour is 60 minutes. And when you do that is 4.9 times 10 to the 6th. Days cancel, hours cancel, and I'm left in gallons per minute. dry this pen is. All right, this one, we're given a distance D in the picture. And we're given that this one is 25 degrees, and we're given that this one is 40 degrees. And I want to find that distance. Okay, I'm going to use opposite over adjacent is going to equal the tangent of the angle. So the opposite side is going to equal the adjacent side tangent of the angle. So for the first one, the distance was given as 16 meters. Tangent of 25 degrees is going to give me 7.7 or 7.46. I'm going to do the same for the other angle. And that's 40 degrees. And that gives me 13.43. Take 13.43 minus 7.46, and that gives me 5.965, and those were all in meters.
7.46 come from the opposite over adjacent.
This is the same thing there. This is the opposite side. So I'm solving for the opposite side for both angles. This becomes the 7.46. This whole distance there is the 13.43. So the difference between the two gives me the x. All right, the next one on this test was vector A plus vector B. A was equal to 2.0i plus 3.5j. B was equal to minus 3.1i minus 4.5j. I take the, and then I had to multiply by 2. So now I've got 2.0i plus 3.5j. And I have a minus 6.2i minus 9.0j. Now I get the result, and that becomes a negative 4.2i minus 5.5j. We've got a cereal box, and it was 0.16 meters times 0.24 meters times 0.050 meters. If I multiply all that together, I get 0.00192 meters cubed. But I want to change it into cubic feet. So what I end up is I have 3.28 feet per meter. I have to cube that, and it ends up being 0.06775 feet cubed, or 6.8 times 10 to the minus 2 feet cubed.
Wood Black? On my version, I did that same process, and I keep coming up with this number, but it said it was wrong.
Well, if you make sure.
It was on version 3. Can I just give you the numbers?
Yeah.
0.2, 0.22,
Okay, so it's 0.2,
0.22.
0.2,
Yeah. And then 0.050.
0.050. If I do point, so I'm going to do it on the calculator. Hopefully you can see it.
Alrighty.
0.22 times 0.2 times 0.05 That gives me 0.0022 times 3.28 times 3.28 times 3.28, and I get 0.0776.
Which is D. On our test.
And what does the Scantron say it's supposed to be?
Should be B.
Should be B. All right, so that's version 3.
Yeah.
If you've got that, holler at me. I didn't catch it.
Alright.
Yeah, send me an email. Okay. And that's version 3.
Number 8.
Number 8. Okay. And my recommendation is send me a picture. That way I can verify it. Okay.
I just did it like just each number and then multiplied it by the.
Well, there's multiple ways of doing it, but that's just an error. And it's possible what I did is when I filled in the key, filled it in wrong.
Yeah, no, you're good.
So, yeah. So if you've got version 3 and you got that one correct, 0.776, take a picture of your Scantron, send me an email, and I'll fix it in Blackboard. Okay, number 10. Number 10 is exactly the same problem I did on Friday before the test. We had a deer that ran 520 meters at 20 degrees. We get to the top. We ran this way at 55 degrees. And we did 380 meters. And that's your resulting vector. And when you go through it, it becomes 11.2 meters per second. So I encourage you to go back and look at the video for a week from the Friday before the test, because it's exactly the same problem. The next one is we got the baseball player throwing up in the air, coming back down. We at a height 3 meters above the release point. We're told that the velocity is equal to 1.25 meters per second. And we want to find the initial speed. This time we use velocity final squared is equal to velocity initial squared minus 2g times the distance. So I'm going to rearrange it. So I'm going to get velocity, my initial velocities, because that's what I'm solving for. V final squared plus 2gd. And now I plug in my numbers. I get 1.25 squared plus 2, 9.8 times 3. This gives you 60.36, and that's in meters squared, seconds squared. Take the square root, and you get 7.77 meters per second. The next one is I've got a rock that's fallen to the ground. We want to know the velocity final at the bottom. I can use V final squared is equal to V initial squared minus 2GH. We're given the height. The height was 35 meters. So the initial velocity, since it was just dropped, is 0. V final is going to equal the square root of 2. And I'm going to, if I put my negative in here, I've got my G, which is 9.8, but I have to use a negative height, otherwise things get funky. And when I do that, I get 26.2 meters per second.
We do the square root, we are taking, is the velocity,
This is V squared.
okay, never mind.
The stone is thrown. Now this time we've got a cliff here. And we're going to throw the stone at a 45-degree angle. And it's going to fall like that. We're given the time of trajectory, 5.5 seconds. And we want to know this distance. That's the distance that we want to know. So the first thing I got to do is get Vx is equal to 9 cosine 45 degrees, and that gives me 6.4 meters per second. Vy is equal to 9 cosine 45 degrees, which is equal to 6.4 meters per second. Distance is velocity times time. That my distance is going to be the x velocity times time. And in this case, that's going to be my 6.4 meters per second times my 5.5 seconds. And that gives me 35 meters. We've got a car puts on the brakes and decelerates. So I've got my little car, our Cushman, and we're traveling at 30 meters per second. Slams on the brakes. We're going to get it 0 meters per second. The time that it took was 11 seconds. Velocity is equal to the velocity initial plus the acceleration times time. We're solving for acceleration, so I get velocity minus my velocity initial is equal to acceleration times time. Velocity minus velocity initial divided by time is equal to my acceleration. And I get 0 minus 30 meters per second divided by 11 seconds. Gives me negative 2.72 meters second squared. So there's my acceleration. Now I want to know the distance. Distance is my velocity initial times time plus 1/2 the acceleration times time squared. So I do my 30 meters per second times my 11 seconds plus 1/2 my negative 2.72 meters per second squared times my 11 seconds squared equals 165 meters. Number 15, we had a position versus time graph. So if I did position versus time, and it says the graph starts at time is equal to 5 seconds, and the velocity of the ball is 0, or the time equals 5. The graph starts at the origin, and at time t the velocity of the ball is 0. We can be positive that the time t at 5 seconds is that the ball has stopped. So you can kind of play with that one. The next one was the walking 6 miles in a straight line north of east. So how I drew my picture is I'm walking in a straight line north of east. And that's 6 miles, or 6 was this was 6 miles. And I end up 4 miles north and several miles east. And we wanted to know this angle. Drawing the picture really, really, really helps. Sine of the angle is equal to opposite over the hypotenuse. We're given the hypotenuse. We're given the opposite. So I'm going to do the sine of the angle. And that's 4 divided by 6. And the angle is going to be the arc sine. And that gives me 42 degrees.
I
Well, got lucky.
I use the inverse tangent.
Well, you don't have a tangent here because you don't know this side. You don't know that side, so I can't use tangent because that's the adjacent side. Okay, we got a bird accelerating from rest, and we're given that the displacement is 34 meters. We're told that the time is 11 seconds. We want to calculate the average velocity. If I do my equations, and we're also told that the initial velocity is equal to 0. So if I do the distance time plus 1/2 AT squared, that's 0. So I end up with 2 times the distance divided by time squared is going to give me my velocity or my acceleration. And that's going to be 2 times 34 divided by 11 seconds squared. That's 34. And that worked out to be 3.1 meters per second. Wait, okay, I've got 2 different equations here. Because that's not acceleration. Hang on. I got my acceleration. I was redoing the wrong problem. Sorry about that.
Question is this.
This is a bird accelerating from rest at a displacement of 34 meters. Time is 11 seconds. I was calculating an acceleration. This was even more straightforward. Distance is velocity times time. You take the distance divided by the time, you get the velocity, and you take 34 divided by 11, that gives you 3.1 meters per second.
I thought the October basically gave you 2 sides, so I just solved for the other.
Okay, now we've got the reaction time. We're going to drop something. We're told that its time is equal to 0.18 seconds. We want to find the distance. Distance is negative 9.8 times 0.18 seconds squared. Gives me 0.16 meters, but the answers were in centimeters, and that was 16 centimeters. Most of you who missed this one and got a lot of partial credit, you gave me 1.6 centimeters. You didn't do the conversion correctly. We got a jetliner that moves due east. So we're flying due east at 455 miles per hour. And we've got a wind that's blowing at 110 miles per hour. Except I didn't draw the picture right. There's 110 miles per hour, and this is a 30-degree angle. And we want to know the resulting vector. The way I did it, because it was easier, is I did 455 in the I direction. I did my vector B as 110 cosine of 30 degrees in the I direction plus 110 sine 30 degrees in the J direction. That gives me the resulting vector of 550I plus 55J. Take my 550 squared plus my 55 squared, and that, if I take the square root of that, it gives me 553, and that's miles per hour. Then you can do the tangent of the 55 divided by my 550, and that gives me 5.71 degrees north of east. Could you scoot that up, please?
This is the jetliner question.
Right, this is the jetliner question. All right, the next one is I've given a circle area is equal to pi r squared. So my first circle is pi r squared. The second circle is pi 2r squared. That becomes 4 pi r. This one, or pi r squared. This is pi r squared. So my answer is 4.
Some people do the easy trick, that's just not being tricked by the times 2, so there's twice the radius, you know.
Alrighty. So, for those of you who did not show your work, a lot of you cost yourself a bunch of points. Because I gave lots of extra credit. Or lots of, not extra credit, but lots of partial credit.
I have a thing, when I said it was my not remember the equation solving it.
Alright. So now, what we were doing, last Friday. What?
This back?
I don't want anything back. Don't want anything back. I don't need the extra paper. Alright. So what we've done so far, and where we were last Friday, see what I got, I'm out of my time. Where we were last Friday is we started looking at Newton's 3 laws. And we said the first law is an object in motion remains in motion, or an object at rest remains at rest unless acted upon by another force. Another force. We talked about Newton's second law, and the general form that we use is that the sum of the forces is going to equal mass times my acceleration, and my force and my acceleration are both vector quantities. And then the third one was that forces come in pairs. The other thing we did is we said that well, that's the general form. We talked about that I can have a force over a unit of time, and that's going to equal a change in my mass times my velocity, and we actually call that a change in momentum, and I don't know why we use the letter P. I have no idea why we use the letter P, but we do. And we said that that gives us, this is another form of the second law. There is, we also talked about the fact that we had two types of forces. We had what we called contact forces. And we had field forces. And my contact force, we could describe something like this. I could take a bat or a tennis racket, and we actually have it, of course, applied to the object. My field force is going to be more like my mass being drawn towards the earth, and this is a force due to gravity. So we have a field force and we have a contact force. So I have a lot of different forces that I have. My forces are directional. So if we look at a little red wagon here, I happen to have a red pen today, so that's good. So I have a little red wagon, and I'm applying a force. and I'm moving in my red wagon along a distance here, the motion that I'm going to get is going to, the motion I'm going to get, depending on how I apply this force, I can have a couple things happen. I can have this force, you know, depending on where how my vector is, I can have a y component and I can have an x component. So we do have to account for the distances, or account for the directions. So very much like when I deal with my velocities, this is why we spend so much time on my vectors, because remember, my vectors are going to have an x component and a y component, and they actually can have a z component as well. This is going to be my y component if I draw it this way. This is going to be my x component if I draw it this way. So I'm going to get a lot of different components that I'm going to have to pay attention to. I also told you that physicists were mean, cruel, and wicked. You know, we just like to be mean, cruel, and wicked. So I have a box on an inclined plane. Okay, have a box on an inclined plane. When you draw, this is why pictures become imperative. Okay, pictures become imperative. So if I have my inclined plane, I have an angle here. If I have my box on my inclined plane, I've got the force due to gravity. And that's usually what we refer to as a weight. And I have it acting down on the box. We say forces come in pairs. I have what we are going to call a normal force. Usually use a little n or a capital N. That's going to be perpendicular to the plane of which I've got. So I've got a normal force, and so I have an equal force that's being applied by the box to the plane. Okay? And I've got a force due to gravity that's going directly down. This becomes a component of my gravitational force. This becomes a component of my gravitational force. Now, if you're good at geometric proofs, okay, if you're good at geometric proofs, you can show that this angle right here is the same angle as that right there. Those are identical angles. Okay, those are the same angles. So I'm going to draw this picture a little clearer so that we can all play with it and look at it. So I have my force due to gravity. I'm going to write it over here. I have my normal force right there. And now I have this component here and this component here. I have two components. This is the angle, and that is the same angle. All right. I'm going to write this out a little differently than the way your book does. Okay? Because typically we write a force, an X force, and we write a Y force. I'm going to write this out a little differently because it's going to help me out in this reference. Okay? Because if I'm on this inclined plane, I have a little bit of a problem there in that my references get a little screwy. So I'm going to use this, and I'm going to define this as the force perpendicular to the plane. So I'm going to actually use that force perpendicular to the plane. And force perpendicular to the plane is going to be my force due to gravity. But here's my angle. So that's going to be the cosine of the angle. Okay, my force perpendicular to the plane is going to be my force due to gravity cosine of the angle. My force due to gravity is going to be the mass times gravity cosine of the angle. Now, the reason I do that, and the reason I do the opposite over adjacent, because if I make my plane flat, that's not typically how we think of a force if we're in that kind of dimension. So I like writing it as being perpendicular to the plane because it helps me keep track of what direction my forces are. This one is my force parallel to the plane. Still going to be my force due to gravity, but now it's going to be sine of the angle, and I get mg sine of the angle. Okay? So if you look at it this way, this is a little opposite of what you normally think about. And you guys did a problem like this in lab. I had a cart going down the slope. And we started at rest, right? So its initial velocity was at rest. And we got down here and we know the distance, right? The distance, well, we're gonna be grins and giggles, and we're gonna say it's a half a meter. And depending on which way you guys did it in the lab, you either got the final velocity at the bottom, right? You either got the final velocity at the bottom, or you got, or you looked at the time, one of the two. But if I did this and I look at the time, so I'm going to do time just because it's going to make it's just going to be a little bit easier to deal with. I'm going to look at time, and we're going to say that the time to do this was 0.25 seconds. Okay? 0.25 seconds. If, and this is why physics builds on itself, right? Physics builds on itself. If I got the time, I can calculate the acceleration. Okay, I can calculate the acceleration. And especially since I know the mass of my cart, and the masses of our carts are typically about 0.5 kilograms, right? Most of them are like 534, 545, you know, they're right in that 500 gram mass. But if I get my acceleration here, I got my acceleration, so I can calculate my acceleration. So if I've got distance is equal to my initial velocity times time minus my acceleration divided by 2, because I'm going to be going down, times time squared. I can calculate that acceleration. And I get 2 times the distance, and that distance is also negative because they're going in the same direction, and we're going to say that that direction is negative. 2 times, because that's 0, 2 times the distance, divided by time squared, is going to equal my negative acceleration. That becomes positive, and I end up with 0.5 meters times 2 divided by my 0.25 seconds squared, and I got a value. I got a value. And I think, if I remember right on this lab, what ends up is you get a slope of the curve, or you got a slope of a velocity versus time graph or something. Because you got a slope. And the number was out there, but look what happens. You actually measured gravity. Because if I'm on this angle here, and I now calculate an acceleration, and I measure this angle, and I know the mass, the force that's being applied is equal to the mass times gravity times the sine, or that one's cosine. No, that one's sine of the angle. And my acceleration that I measured, it has to equal gravity times the sine of the angle. You actually measured gravity dealing with that inclined plane problem. It's distorted a tad because I have to deal with my angle, but as I changed this angle up here, it was going to be pretty constant, and I could actually calculate what my average gravity, so you could actually calculate gravity that way. Which is one of the reasons why we like that lab. One of the reasons why we like the lab is because you can actually measure gravity. And turns out you measure gravity several times in the... Okay, let's do one other thing because you guys have been doing it in lab or are about to do it in lab. So I've got a hockey puck, a block, whatever. I'm going to apply a force.
Inside of the table.
And that force is, we're going to go ahead and give it a 5 Newton pull. We're going to give it a 5 Newton pull. And we also know that I have a force due to gravity, mass times my acceleration due to gravity. And we have a normal force. We have a normal force. Thing about our normal force is these two forces are the only forces in the y direction. And my block isn't moving up or my block isn't moving down. So I can do the sum of the forces in the y direction. Going to equal the mass times my acceleration. I've got my normal force pointed up. I have my force due to gravity pointed down. I have to keep track of my direction, okay? I have to keep track of my direction, so my picture's really, really going to help. But because I've got no motion in the y direction, I have no acceleration in the y direction, and so my normal force minus my force due to gravity is going to be equal. So that's how we normally write to sit there and say, well, what's my normal force, or what's the magnitude of my normal force? It's because I have no motion in the y direction. I can make that 0, and I can show that my normal force is equal to the mass times gravity. Now, we also know that there's a resistance to this motion. Okay, there's a resistance to the motion. Force in and of itself is a measure of the resistance to the motion. And that's one of the things that we talked about, inertia. There we go. I think that's right. Inertia just didn't look right all of a sudden. And that my inertia is related to my mass. So if I'm applying a 5 Newton force, I'm not going to something that has a mass of 1.5 kilograms is going to be different than what I'm going to get if I have something that's 0.25 kilograms, because it's related to the mass, and that's the force is going to be related back to that inertia. So I've got the more mass it has, the more inertia it has, and I have to take that into consideration. But we also know that there's something else here, and it's something else that's related to the fact that I have two objects, and if I did this on bare wood with a sandpaper surface, I get the force that's applied is going to be resisted by what we call a force due to friction. And we usually use a script F to refer to that force due to friction. And people have played with it enough that they know that the force due to friction is going to be this little letter mu times my normal force. And a lot of times we use the capital N just so that you remember that friction is fun. Okay, friction is fun. So that's kind of how you can remember that equation, that we get friction is fun. But my force due to friction is out there. Now, we all know, because it's fair time, and my favorite event at the fair is horse pulls. Or you can go to the tractor pull. I just like watching the horses because the horses are pretty explosive. Tractor's not near as much fun to watch. You know, the horses, when you see those horses that get ready and bear down and they drop the pin on the sled, those horses are ready to pull that sucker, and they really explode. But they're trying on that sled, and if I look at that sled for a tractor pull or a horse pull, I've got what they call a dynamic sled, okay? I got a dynamic sled, and I've got a huge mass here, and the reason the horses have to explode is because in order to get this thing moving, they've got to overcome a force due to friction. And I've got to overcome a force due to what we call static friction. And my static friction, we usually write it with a little script S. And my static friction is always going to be greater than what we call kinetic friction once I get it moving. And anybody who's tried to get anything going that always knows that the hardest part is to try and break that static friction. So if I'm doing the world's strongest man competition and I'm getting them to pull a train, it's getting that train started that's the hard part. Once I get it moving, it's a lot easier to pull. Dynamic sleds don't work that way. Dynamic sleds actually get harder to pull because they change how the masses are distributed, and it causes a problem for the dynamic sled for the horse pull. But I get that force due to friction. So we look at these forces due to friction, and we're going to have to overcome that. So I can have force due to static friction, or I can have forces due to kinetic friction. And this is my friction of motion. And this is my friction of trying to get it started. And you can kind of see the difference this way. So I'm actually going to do it through the document cam. So I got a cardboard piece of board here. I got my handy dandy calculator here. So I got it sitting on there. I got my handy dandy calculator. I'm going to do it this way. And my force due to static friction is going to keep my calculator on the board until all of a sudden it starts sliding. Now, I can actually measure, and this is one of the ways that we measure the difference between static and kinetic friction. I'm going to do this board because it's a little easier. So I can actually raise it up and I can measure that angle, and I can find out when my mass of my calculator overcomes the static friction to ultimately slide down. So I can measure static friction as well as kinetic friction, and we can play with those and go back and forth. So that's one of the forces that we have. I'm going to introduce one more force so that so now you guys are starting to see that we've talked about a bunch of concepts so that you can start doing the homework and getting those extra credit points on the homework. But there's another force that's out there because we know what happens, okay? So now we introduce another fun thing that physicists like to play with. I have a spring, okay? I have a spring. And we can do a plot here. And this is going to be stretch. And it's going to be force. So I'm going to put a mass on my spring. And it's going to have an initial length x. Okay, I'm going to put a mass on my spring. And we know what happens when I put a mass on my spring. It stretches. So I put a mass on my string. This is mg. and I'm going to get a new length. I'm going to get a change in the length, and that change in my length is going to be what we refer to as the stretch. And if I have a nice perfect string, I apply a force, I get a stretch. 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 I get a nice straight line. The slope of that line is going to be Newton meters, okay? Because my forces are in newtons, my stretches are in meters. I get Newton meters, and it's a constant for the spring that I have. Different springs are going to have different constants. And I get a nice straight line. And this is what's known as Hooke's law. Okay, that's known as Hooke's law. And we usually write it like this. I get Hooke's law is the force is going to be minus kx, where x is my stretch. Okay, that's my stretch. This k is related to the spring that I'm using, and it's a spring constant. And it's a function of the spring that I have. The negative comes from the fact that we're usually doing this. We're usually hanging the spring, and we're usually dealing with the direction. And my change in x, actually, if I'm dealing with this in this direction, it's a negative. And the spring really wants to return back to its normal shape. So we end up with Hooke's law looking like this. Now, the good news is we usually use the magnitude of it. And so my magnitude of my force associated with the spring is usually kx. So but again, the question is where the direction of the force is. My spring is resisting it. I've got a force due to gravity, which is where this negative is coming from. Because we know that I've got my stretch that I have there. And that's Hooke's law. Now, Hooke's law, I love how we do this. This is one of those cases where we've got a law that it only works during certain spots. Because if I have a rubber band, right? I got a rubber band. If I do a rubber band and I do this, I can put force on it, push on force on it, and nothing really happens, and then all of a sudden I'll get to a nice straight spot, and it'll obey Hooke's law for a little while, and then if I put too much weight on it, it starts to deform, and it doesn't come back to its normal shape, and then ultimately it'll break, and I can have something that looks like this. This is a normal material behavior. Most materials will have a region where it will obey Hooke's law, but then most of the times I'll get deformed. So if I do what we call a little dog bone, and we pull a little dog bone and do this, it's going to follow a very similar behavior, but ultimately, no, if I pull it off, I get these little deformations in there as I pull. And ultimately, it will break, so that we end up getting it to break. So I've got Hooke's law, and that's another piece. I'm going to stop there. We'll start working some problems on Friday. But this gets you a long way to get the material that you need for starting to work on homework problems. The registrar. Yeah, and just drop